Hello students, welcome back to the next session. In this, we are going to see the problems, numerical problems on reversed Carnot cycle. In earlier session, we have discussed the theory behind reversed Carnot cycle, and problems will be very simple if you understand and apply the correct formula for a particular task given in the problem. So please understand the problem statement correctly, and then you can easily solve the problems. And let me discuss a few problems, and I will give you these problems and solutions. A few exercises I will post in your Google Classroom. So these are the topics we are seeing all through in this first unit. Introduction to refrigeration, and unit of refrigeration, COP, ideal cycles. We have reversed Carnot cycle, Bell-Coleman cycle, and refrigerants, their desirable properties, classification nomenclature. We are going to see the problems today on reversed Carnot cycle. In next session, we are going to start Bell-Coleman cycle. We are going to see its theory, and then we will solve problems on this. And one more session I need to discuss about desirable properties of refrigerants and classification nomenclature. All three can be completed in single session. I need 2 sessions for Bell-Coleman cycle and 2 sessions, one session for refrigerants. So that is the plan for this first unit. So this is the first problem, students. Study the problem carefully. A machine working on a Carnot cycle operates between 305 Kelvin and 260 Kelvin. So here you are both temperatures are given, higher and lower, and determine the COP when it is operated as. First one is refrigerating machine, a heat pump, a heat engine, and we have seen in earlier session the relationship of COP between all these three, and the relation I suppose all of you could have remembered and apply that. It is very simple problem. It is a 5 mark question only. So given temperatures are, higher temperature is 305, that is why it is T2, and lower temperature is T1, it is 260 degree Kelvin. So first is a refrigerator machine. When this machine operated as refrigerating machine, then we know that the COP of a refrigerator machine is T1 by T2 minus T1 equal to, so 260, 305 minus 260, it is 5.7H. So that is the COP of refrigerator machine. Very simple answer, very simple question and answer. And the next second part is a heat pump, COP of heat pump. COP of a heat pump, it is equal to T2 divided by T2 minus T1. So that is 305 divided by, so here it is T2. In the case of refrigerator, it is T1. So 305 divided by 305 minus 260, it is higher. So you can remember COP of a pump is equal to COP of a refrigerator plus 1. So here you can see the difference. It is exactly plus 1. 5.7H plus 1 is equal to 6.78. So this is the COP of pump. So next we have to compute the COP for heat engine. So heat engine is T2 minus T1 divided by T2. So here it is 305 minus 260 divided by 305. So this is the COP of heat pump. So heat pump is very less, 0.147, and when you compare all these three COPs, COP of heat pump is higher, and next is refrigerator, and then heat engine. Heat engine is always lesser COP. So by this way also you can cross check your answer, students. So we will move on to next problem. A Carnot refrigeration cycle absorbs heat at 270 Kelvin and rejects it at 300 Kelvin. Calculate the coefficient of performance of the refrigeration cycle. If the cycle is absorbing 1130 kilojoules per minute at 270 Kelvin, how many kilojoules of work is required per second? So the work should be calculated in terms of seconds. If the Carnot heat pump operates between the same temperature as the above refrigeration cycle, what is the coefficient of performance? So here for heat pump we have to calculate, and how many kilojoules per minute will the heat pump deliver at 300 degree Kelvin if it absorbs 1130 kilojoules per minute at 270 K, that is Kelvin. So these are the four questions we have to solve here, and first we will list down what are all the given data. So given is T1 lower temperature is 270 and T2 equal to 360 Kelvin, 300 Kelvin. So first task, calculate the coefficient of performance of this refrigeration cycle, and here it is T1 divided by T2 minus T1. It is simple. 270 divided by 300 minus 270, it is 9. So that is the answer. Whereas heat pump 9 plus 1 equal to 10, and then the COP of heat engine is 1 by 10, it is equal to zero point 0.1 is the COP. COP is very less in case of heat engine. And second task, work required per second. So we have to calculate work required per second, and let the work required per second equal to WR, and the heat absorbed at 270 Kelvin, that is T1. T1 is 270 lower temperature. So Q1 is given in the problem, that is 1130 kilojoules per minute. So if you convert that into seconds, 1130 divided by 60 equal to 18.83 kilojoules per second. So this is the given data and we are converting into in terms of seconds. Then COP of R equal to Q by W. So Q by W is WR. So this is, we know it is 9. In previous slide we have calculated this, and Q1 is 18.83 we have calculated per second, and WR is unknown, so we can calculate WR is equal to 2.1 kilojoules per second. So that is the second task is accomplished. So 2.1 kilojoules per second. And then we have to calculate the Carnot pump, that is the coefficient of performance of Carnot heat pump. So here next we calculate the third task and fourth task. If the Carnot heat pump operates between the same temperatures as the above refrigeration cycle, what is the coefficient of performance? So we have to calculate the heat pump. Already we have done that. It is 10 in first statement itself. So that is 10 answer. And heat delivered by heat pump, we can calculate either T2 divided by T2 minus T1. Otherwise, the refrigerator COP plus 1. So both ways you can calculate, no problem. Heat delivered by heat pump at 300 Kelvin is equal to Q2 equal to heat delivered by the heat pump at 300 K. Heat absorbed at T 120 K, that is T1. So Q1 is given 1130 kilojoules per minute. So COP of pump is equal to Q2 divided by Q2 minus Q1. So substituting these values, we know COP, and we know Q2. Q2 is unknown, and we know Q1. It is given 1130 kilojoules per minute. So substituting this, Q2 10 Q2 minus 1130 equal to Q2. So here 9 Q2 equal to 1130 and then the Q2 is equal to 1256 kilojoules per minute. So this is the answer for Q2, that is the heat pump, the how many kilojoules per minute. That is the fourth task we are calculating as 1256 kilojoules per minute. So this is the problem number 2, and then we will move to next problem, students. Next problem, problem number 3, we see here a cold storage is to be maintained at -5 degrees Celsius. It is given in Celsius, not Kelvin, while the surroundings are at 35 degrees Celsius. The heat leakage from surroundings into cold storage is estimated to be 29 kilowatts. So 29 kilowatt is given. The COP of the refrigeration plant is one third of an ideal plant working between the same temperatures. Find the power required to drive the plant. It is a very simple problem, and you can see here this is the refrigerator, refrigerating plant, and T1 at T1 it is T1 equal to 268, 273 minus 5, 268, that becomes the T1, and T2 equal to 35 plus 273, it is 308 Kelvin. So Q1 is to refrigerator, Q2 is from refrigerator to surrounding. So this the problem statement, and simplified in this diagram. So T1 is equal to 268 and T2 equal to 308 degree Kelvin. So this is the given problem, given data in the problem. Q1 equal to 29 kilowatt. So Q1 is given 29 kilowatt in the problem statement, that is 29 kilowatt. And we know that the coefficient of performance of an ideal refrigeration plant is T2, T1 divided by T2 minus T1. So that is 268 divided by 308 minus 268. It is 6.7. COP of ideal plant is ideal refrigeration is 6.7. Since the actual coefficient of performance is one third, so it is given the actual is one third only. So we have to convert to one third, and one third into 6.7, it is 2.233. So this is the actual coefficient of performance for the plant, refrigeration plant. Also, we know that the actual COP equal to Q1 divided by R. So we know Q1, that is 29 kilowatt, and WR is unknown, that can be calculated, and WR equal to Q1 divided by COP actual. So 29 divided by 2.233 is the your COP. So that is, sorry, work of the actual refrigerator, and this is equal to 12.987 kilowatt. So Q work is work here, WR2 refrigerator is to 12.987. So this much is required. So that is the answer for this question. So we will move to next problem. I wanted to show you, and I wanted to solve here different kinds of problems. So this is the problem statement, example 4. Two refrigerators A and B operate in series. So two refrigerators are connected in series. The refrigerator A absorbs energy at the rate of 1 kilojoules per second from a body at temperature 300 degree Kelvin, and rejects energy as heat to a body at temperature T. The refrigerator B absorbs the same quantity of energy which is rejected by the refrigerator A. So whatever energy it gives A, so that becomes input to the next refrigerator, that is B. From refrigerator A from the body at temperature T, and rejects energy as heat to a body at a temperature 1000 Kelvin. If both the refrigerants have the same COP, so COP is the same here, that is given. Calculate the temperature T of the body, the COP of the refrigerators, and the rate at which energy is rejected as heat to the body at 1000 degree Kelvin. So this is the problem, a very simple problem, 3 tasks only we have to calculate, that can be done very easily. And here you can see, so this is the Q1, this is the refrigerator A, and WA is operating this refrigerator A. So that is Q1 is 300 degree Kelvin. From 300 degree Kelvin, you have this heat energy, and Q2 is Q1 plus WR, and here, sorry, WA, and we have this series, right? We are connecting these two in series, and now this is the temperature. This is the temperature, and we have Q3 equal to Q2. So this is refrigerator B that is driven by work B, and Q4 equal to Q3 plus WB. So that is 1000 degree Kelvin we are getting at the outlet of the refrigerator B. So two are connected in series, A and B, and this is simple schematic with which the given data can be presented. So Q1 equal to 1 kilojoules per second. So that is given in the problem. So Q1 is heat absorbs. Refrigerator A absorbs energy at the rate of 1 kilojoules per second. That is Q1. And T1 is 300 degree Kelvin. So that is 300 degree Kelvin. T2 equal to T, and T3 equal to 1000 degree Kelvin. So T2 equal to T. So T2 is equal to T here, or we can directly write T2 here, nothing wrong, and T3 equal to 1000 degree Kelvin. So the arrangements are as shown in the figure, and temperature T of the body temperature we can see here. The COP of refrigerator A, T1 divided by T2 minus T1, so that is 300 divided by T minus T2 equal to T only, so 3 T minus 300. So COP is unknown and T is also unknown. So COP of A, and also it is given that COP of A is equal to COP of B, both are same, and the COP of B is COP of B here T2 divided by T3 minus T2 equal to T divided by 1000 minus T. So here COP of A is equal to COP of B, so we can equate these two, and 300 only T is unknown, so T is unknown, and we can easily find this T. So by solving these two, we can get T is equal to, so T is equal to T equal to 547.7, a simple calculation only. So here T equal to 547.7 K. This is the first answer. And then COP of the refrigerators. So now we know T. So T we know it is equal to T2, and we have to calculate COP. And it is easy now. We can substitute in the first equation or second equation, we can get it. So COP of A equal to COP of B equal to 300 divided by 547. So this we know now, and minus 300 equal to 1.21. So this is the COP of refrigerator A as well as refrigerator B. So 1.21 is the answer for the second part. So third part, rate at which energy is rejected as heat by the body at 1000 degree Kelvin. We know that the work done by refrigerator A, so WA equal to Q1 divided by COP A. So COP of A equal to Q1 divided by WA, that we know. From that we are rearranging this, and 1 by 1.21 is equal to 0.826 kilojoules per second. So if you need for refrigerator A, so Q2 can be calculated, Q1 plus WA equal to 1 plus 0.826, so that becomes 1.826 kilojoules per second, so that becomes Q2. So Q2 also now we have found, and now the work done by the refrigerator equal to Q3 divided by COP of B equal to 1.826 divided by 1.21, so that is equal to 1.51. So Q3 equal to Q2, so 1.826 can be substituted, and 1.51 kilojoules per second can be is the answer for WB. So work done for B refrigerator and then heat rejected to the body at 1000 degree Kelvin. So that is equal to Q4. So Q4 is equal to Q3 plus WB. Q3 plus WB. So that is equal to 1.826 Q3, or it is Q2 also. So Q3 equal to Q2 and 1.51, that is WB, and that is equal to 3.336. That is the rate at which the energy is rejected as heat by the body at 1000 degree Kelvin. So this is the final answer for third task, and this is a very simple problem. You have to understand thoroughly and you have to do this. Since COPs are equal, so COP of A and B are equal, it is very simple problem. And if it is different, we have to work a little more and we can find out that also. So coming to fifth problem, a refrigerating system operates on the reversed Carnot cycle. The higher temperature of the refrigerant in the system is 35 degree Celsius, and the lower temperature is minus 15 degrees Celsius. So T1 is minus 15 degrees Celsius and 35 degree Celsius is T2. The capacity is 12 ton of refrigeration. Determine COP, heat rejected from the system per hour, power required. So these are the three tasks we have to do. And first list down the parameters given. T2 equal to 35 degree Celsius, so that is 308 degree Kelvin. T1 equal to minus 15, so that becomes 258 K. So Q1 equal to 12 ton of refrigeration equal to 12 into 210. So 1 ton of refrigeration is equal to 210 kilojoules per minute. So that is 12 into 210, so 2520 kilojoules per minute. The refrigerating system operating on the reversed Carnot cycle is shown in this figure. So here you can see this is the T1 and this is Q1 and this is R. R is given the WR. So this is Q2 is equal to Q1 plus WR, that is equal to T2. So this is higher temperature. So this we know, and both temperatures we know here. And when you see this temperature entropy curve, so this is 1, 2, 3, 4. It is our usual curve, and with this we can solve this problem. So first one is COP. COP of refrigerator T1 divided by T2 minus T1. So that is equal to 5.16. Heat rejected from the system per hour is equal to the WR be the work or power required to drive the system. So WR can be calculated from this equation. COP of R equal to Q1 divided by R. So WR can be Q1 divided by COP of R. So 2520 divided by 5.16 equal to 488.37 kilojoules per a minute. So now with this, heat rejected from the system can be calculated, that is Q1 plus WR equal to 2520 plus 488.37, that is equal to 3008.37 kilojoules per minute. So Q2 equal to, so this is per minute, you just convert into per second, per hour. So that is into 60, that equal to 180,502.2 kilojoules per hour. So this much per hour. Power required is third task. WR equal to 488.37 kilojoules per minute. So 488 divided by 60 equal to 8.14 kilojoules per second, or we can say it is kilowatt also. Kilojoules per second equal to kilowatt otherwise. So this is the power required. So we have done now. We have calculated all three tasks. So it is a very simple problem. So coming to next problem, 1.5 kilowatt per tonnage of refrigeration is required to maintain the temperature of minus 400 degrees Celsius in the refrigerator. If the refrigeration cycle works on the Carnot cycle, determine the following. First one is COP of the cycle temperature of the sink, heat rejected to the sink per ton of refrigeration, heat supplied, and EPR. EPR is nothing but energy performance ratio. It is also COP only. COP if the cycle is used as a heat pump. So heat pump, it is heat pump COP we have to compute here. So very simple problem, students. Now same Carnot reversed Carnot cycle is applicable here. So given data is equal to WR 1.5 tonnage, that is kilowatt, 1.5 kilowatt, and Q1 equal to 1 tonnage of refrigeration. So that is 1 tonnage of refrigeration. T1 equal to minus 40 degrees Celsius. So that is 233 degree Kelvin. And the COP of the cycle, it can be shown like this. Since 1.5 kilowatt per ton of refrigeration is required to maintain the temperature in the refrigerator, the amount of the work required to be done is like this. So this is the simple schematic, and you can see the TS diagram. And T1, it is cold body, and this is Q1, and WR required by this refrigerator, and we have Q2, that is heat rejected, and Q1 plus WR, so that is T2, so that is sink, and cold body temperature is T1 and sink temperature is T2. So with this we can easily solve this. So WR equal to 1.5 kilowatt, and this is kilowatt is nothing but kilojoules per second, and 1.5 into 60, so that is 90 kilojoules per minute. And heat extracted from cold body, so that is equal to Q1 equal to 1 tonnage of refrigeration, so that is equal to 210 kilojoules per minute. In earlier session, I have given you a table of 1 tonnage of refrigeration equal to many number of units. So in accordance with the many number of units, I have given you values, and definitely you should remember that. From that you can see it is 1 tonnage of refrigeration equal to 210 kilojoules per minute. And COP of R equal to Q1 by WR, so that is equal to 210 divided by 90. So that is the first part. COP of refrigerator equal to 2.33 is the answer. So coming to next part of the question, so that is temperature of the sink. Let T2 be the temperature of the sink. So we know that COP of R equal to T1 divided by T2 minus T1. So we know 2.33, that is the COP of R, and 233 divided by minus 2 T2 minus T23. So we will be getting T2 value. So T2 is equal to 333 Kelvin, 333 Kelvin, and T2 equal to 60 degree Celsius in terms of Celsius, and the heat rejected to the sink per tonnage of refrigeration. So this is the next part of our problem. We know that the heat rejected to the sink equal to Q2 equal to Q1 plus WR. So that is equal to 300 kilojoules per minute. So coming to last part of this question, that is the EPR, energy performance ratio. It is nothing but COP only. So we know that the heat supplied when the cycle is used as heat pump, it is Q2 equal to 300 kilojoules per minute, and energy performance ratio equal to COP. So this is the pump COP equal to COP R plus 1, 2.33 plus 1 equal to 3.33. So it is a very simple computation. We can easily calculate this. So it is equal to 3.33 is the COP of pump. So that is the problem, and we have solved all the 4 tasks given here, and we will move to next problem. So coming to next problem, it is the capacity of a refrigerator is 200 tonnage of refrigeration when working between minus 6 degrees Celsius and 25 degrees Celsius. Determine the mass of ice produced per day from water at 25 degrees Celsius. Find the power required to drive the unit Assume that the cycle operates on the reversed Carnot cycle and the latent heat of fusion of ice is 335 kilojoules per kg. So these are the given data, and we can easily calculate these two tasks. So given data is equal to, that is Q equal to 200 and tonnage of refrigeration, T1 equal to minus 6 degrees Celsius, so that is equal to 267 Kelvin, and T2 equal to 25 degrees Celsius, that is equal to 25 plus 273 equal to 298 Kelvin. And latent heat of fusion is also given, so that is HF, that is latent heat of fusion is represented by HF of ice equal to 335 kilojoules per kg. Mass of ice produced per day, we know that heat extraction capacity of the refrigerator, that is Q equal to 200 into 210, so that is equal to 42,000 kilojoules per minute. So 1 TR equal to 210 kilojoules per minute, and 1 kg of water at 25 degrees Celsius equal to 0 degree Celsius. So this can be calculated. Energy required, mass into specific heat. So specific heat into temperature drop plus latent heat. So this is the energy required, and it is 1 into 4.187 into 225 minus 0. So that is equal to 25 plus 335. So that is equal to 439.7 kilojoules per second. So this is the given 1 kg of water and energy required. So energy required is 439.7 kilojoules per kg. So mass of ice produced per minute equal to 42,000 divided by 439.7 equal to 95.52 kilograms per minute, and mass of ice produced per day equal to, we have to convert into 24 hours, so that is 137.55 tons. So that is 137.550 kg. So that is divided by 1000 equal to tons. So that is the tonnage mass of ice produced per day, and power required to drive the unit. We know that the COP of the reversed Carnot cycle is equal to T1 divided by T2 minus T1. So 267 divided by 298 minus 267, that is equal to 8.6. And COP equal to heat extraction capacity divided by work done per minute. This way also we can calculate. So now from here we can get this WR. WR can be calculated. So that is 42,000 divided by 8.6, that is equal to 4,884 kilojoules per minute. So that can be converted into seconds. So 81.4 kilowatts is the answer. So that is the power required to drive the unit. Coming to next problem, 500 kilograms of fruits are supplied to a cold storage at 20 degrees Celsius. The cold storage is maintained at minus 5 degrees Celsius, and the fruits get cooled to the storage temperature in 10 hours. Given a latent heat of freezing is equal to 105 kilojoules per kg, specific heat of fruit equal to 1.256 kilojoules per kg degree Kelvin. Find the refrigeration capacity of the plant. So this is again a simple question only. So here 500 kilograms, that is mass. T2 equal to 20 degrees Celsius, 20 plus 273, and T1 equal to 268 Kelvin. HF equal to 105 kilojoules per kg. CF is equal to 1.256, that is the specific heat of fruit, kilojoules per kg degree Kelvin. We know that the heat removed from the fruits in 10 hours equal to MC into T different delta T, that is T2 minus T1. So that is 500 into 1.256 into 293 minus 268. So that comes 15,700 kilojoules. So the latent heat of freezing is equal to mass into HF. So that is 500 into 105 equal to 52,500. Total heat removed in 10 hours. So you have to calculate for 10 hours. So that is for Q1 plus Q2 equal to 15,700 plus 52,500 equal to 68,200 kilojoules. So this is the heat removed from the fruits in 10 hours. So coming to next problem, a cold storage plant is required to store 20 tons of fish. The fish is supplied at a temperature of 30°C. So given that specific heat of fish above freezing point equal to 2.93 kilojoules per kg degree Kelvin, and specific heat of fish below freezing point equal to 1.26 kilojoules per kg Kelvin. The fish is stored in cold storage at -8°. Freezing point of fish is -4°C. Latent heat of fish equal to 235 kilojoules per kg. The plant requires 75 kilowatts to drive it. So we have to find the capacity of the plant and time taken to achieve this cooling. So two things we have to find. Assume actual COP of the plant as 0.3. So of the Carnot COP. So it is 0.3 of Carnot COP. So we have to convert into 0.3. So this is the given data, students. M equal to 20 tons. So that is 20,000, right? So 20,000 kgs, and T2 equal to 30°C equal to 30 plus 273, 303 degree Kelvin. CAF. So CAF. So this is a specific heat of fish that is equal to 2.93 above freezing point. This is actually above freezing point, 2.93 kilojoules per kg Kelvin. So below the freezing point, that is equal to 1.26 kilojoules per kg Kelvin. So TF, that is TF is equal to -4°C. So that is equal to 269. T1 equal to 265. So HF specific heat of fish is 235. Sorry, latent heat of fish is 235, and P equal to 75. Power is 75 kilowatt. So that is kilojoules per second. Capacity of the plant COP can be calculated. T1 divided by T2 minus T1 equal to 265 divided by 303 minus 265, that is equal to 6.97. Actual COP equal to 0.3 into 6.97. So that is equal to 2.091. So heat removed by the plant is equal to the work required to that is actual COP into work required, that is 2.091 into 75 equal to 1 that is 156.8 kilojoules per second. So that is per second we are converting into per minute. It is equal to 9408 kilojoules per minute. And the capacity of the plant is equal to, we can calculate that is ton in terms of tonnage. In terms of tonnage, we are calculating this 9408 kilojoules per minute divided by 210. So 210 equal to 44.8 the tonnage of refrigeration. So that is the capacity of the plant. So tonnage of refrigeration gives you capacity of the plant, refrigeration plant. So that is a very simple problem. And then we have to calculate time taken to achieve this cooling, right? So thus that also we need to calculate. Heat removed from the fish above freezing point equal to Q1 equal to M into CIF into T2 minus TF, that is 20,000 into 2.93 equal to 303 minus 269, that is equal to 1.992 into 10 to the power of 6 kilojoules. Heat removed from the fish below freezing point. So Q2 equal to M into CBF into TF minus T1. So that is 20,000 into 1.26 into 2.69 minus 265. So that is equal to 0.101 into 10 to the power of 6 kilojoules. We have to find the total latent heat of freezing, so that also can be calculated here. So mass we know, and HF fish also we know, so that is equal to 4.7 into 10 to the power of 6, and the total heat removed by the plant is equal to Q equal to Q1 plus Q2 plus Q3. So all energies, heat energies we have to add here. So that is equal to 6.793 into 10 to the power of 6 kilojoules. Time taken to achieve this cooling is equal to total heat removed by the plant divided by heat removed by the plant per minute. So that is equal to 6.793 into 10 to the power of 6 divided by 9408 equal to 722 minutes required. So in terms of hours, it is 12.03 hours are required for achieve that cooling. So this is the answer, students. So we have seen the wide varieties of problems, and I will give you a few more questions, exercise questions, and all of you solve those questions, and you can submit via Google Classroom also. We stop here, and then bell column and cycle we will start in next session, students. So these are the books, and as I said, Kurmi is the very good book, very simple, and also you can refer CP Arora and RK Rajput. This is also good. Apart from that, Balani also you can refer. So these are the books, students. We stop here, and we will meet in next session where we are going to start the next ideal cycle. Thank you, students. Thank you.